In the following videos, we'll be moving a little bit away from Excel and into R just for practicality purposes and ease of computing. While all of these things are possible to do in Excel, they're not exactly practical to do for reasons that I'll illustrate. So, we're going to be computing some z-tests and some t-tests in R. And for these tests, we're going to need a package called BSDA. So once you install that and run the library loading those functions, we'll be able to continue. So, for the z-test, we'll need to extract a sample mean, a sample standard deviation, and a sample size from the one sample data. So, for our z-test, in our z-test data, we have a variable called x, and these are our data, and there's 20 observations, and these are our data scores of x. So, we'll need to compute a sample mean for x. And to do that, we're going to create an object called sample mean and store the mean of x in that object. And we have our sample mean, 3.65. We're going to do the same for the sample standard deviation. And we're going to create an object called sample size and just store the number of rows or the number of observations in that object called sample size. Now, our hypothesized population mean for this example is 4.5, and our z-test is going to determine whether our sample mean significantly differs from our population mean, or whether our sample mean is likely to be able to generalize to our population mean, or rather, if they're the same. So our population mean is stored as being 4.5. So we can perform our one sample z-test using this function that is embedded in the BSDA package. The function is just z.test. X is our variable that we're using to perform the test, which is just variable x in our z-test dataset. Sigma.x is our sample standard deviation, which we have stored in a value called sample_SD. So we'll just type that here. Our population mean, mu, is stored in an object called population mean. So we just type that here. Alternative is always two-sided by default for this test in R. So if we run this line, we'll get an object called z-test result. And to print our summary, we just do print z-test result. And here we have our summary for our result of our one sample z-test in R. Our p-value is 0.9. And our 95% confidence interval is between these two numbers. Our alternative hypothesis is that our true mean is not equal to 4.5. And our p-value of 0.09 indicates that this test was not statistically significant. This means that we don't have enough information to reject the null hypothesis. And so we are going to fail to reject the null hypothesis that the means are not any different. Moving on from z-tests to t-tests in R, there are several different kinds of t-tests that you can do, and we're going to load in our data for each of these. We're going to do a one sample, a two sample, and a paired sample t-test in R, and I'll show you how easy these are. So, we just loaded in our three data sets called one samp, two samp, and pair samp. And these data are just listed as X. These are just some scores that we have. Let's call them test scores, maybe. Yeah, exam 1, exam 2, and we have a difference between them. And we have our two sample t-test. Those are all of our data frames and what they look like. And what we're going to do is set our options to SciPen equals 999. And what this does is it just makes the scientific notation expand to up to 999 characters. So that when we get extremely small decimals, like p-values sometimes are, it'll actually show us the entire thing instead of R condensing it into scientific notation that we can't really read. So, the function for t-tests is just t.test. and we can run that on our data by just typing t.test parentheses 1samp. So this is going to be a 1-sample t-test. And when we run this function, we do a 1-sample t-test. Our p-value is obviously very small, which is why we switched our scientific notation option. And our p-value is statistically significant. It is much, much, much less than 0.05. And so, in this case, we can reject our null hypothesis that our mean is equal to 0. And we fail to reject our alternative hypothesis that our mean is not equal to 0. For our 2-sample t-test, we are determining whether the means of these samples are statistically different or not. So, our null hypothesis is going to be that the means are not different, and our alternative hypothesis is going to be that they are different. So when we perform our 2-sample t-test here, we're going to use our 2-sample data set. And in this data, we have 2 samples, sample T and sample C. So, for the 2-sample, we have to assume that the variances are equal, which is an assumption that t-tests have that's just underlying. So, we're going to do t.test, 2samp column T, and 2samp column C. And when we run that, we have a 2-sample t-test. We have our p-value, 0.03. And we have our alternative hypothesis that the difference in means is not equal to 0. Because our p-value is less than 0.05, it is significant at a confidence level of 95%. So, what that means is that our means are, in fact, significantly different, and we can reject our null hypothesis that they are not different. We fail to reject the alternative hypothesis. The true difference in means is different, it is not 0. Finally, we're going to do a paired sample t-test. Now recall that the paired sample t-test has to do with a sample where one of the samples has some effect or has a hypothesized effect on another. So in this case, we have some exam scores, and we're trying to see whether the average of the exam scores from exam 1 to exam 2 are different, and how different they might be. So we're going to do a t-test, and we're going to use our paired sample data set, and we're going to use the column exam 1 and compare it to the column exam 2. And we're going to tell R that this is a paired t-test. So we're going to set paired equals true. And when we run this function, we're going to get a p-value of 0.06. This test was not statistically significant, and we do not have the evidence to reject the null hypothesis that the means are not significantly different. Therefore, we find, during this paired t-test, the difference in the average score from exam 1 to exam 2 does not significantly differ. And that is how you perform z-tests and t-tests in R.